Welcome, my friends! In this video, we will introduce the chi-square distribution and discuss the chi-square goodness of fit test and how the test can be completed using the TI-84 calculator. We will discuss the by-hand procedure, but as the test is calculation intensive, we will be using the TI-84 calculator functions to do most of the work. First, let's talk about the chi-square distribution, which you may or may not be familiar with. Chi is a Greek letter which looks an awful lot like the letter X, but is shaped slightly differently if you look very closely. Like the Z and T distributions, the chi-square distribution is a continuous probability distribution used in many hypothesis tests. The distribution only takes on positive values as it consists of squared numbers. The distribution is skewed right, as can be seen from the graph. This contrasts the chi-square distribution from the Z and T distributions, which are both symmetric. Like the student's T distribution, the shape of the chi-square distribution depends on the degrees of freedom. We will talk about how to calculate the degrees of freedom when we look at an example. Also like the student's T distribution, as the degrees of freedom increase, the chi-square distribution starts to look more like the normal distribution. Finally, all hypothesis tests performed with the chi-square distribution are right-tailed tests, so the p-value will always be in the right tail of the distribution. The chi-square goodness of fit test is associated with distributions in this form, where there are a number of different categories that each have a specified percentage chance of occurring. You can think of the second column as the probability that a randomly selected individual from this population falls into the associated category. Of course, all the percentages should add up to 100 for this to be a valid distribution. An example of a distribution that might be used in the chi-square goodness of fit test might be the distribution of ages in a particular city. According to Michigan demographic statistics, the age distribution of individuals living in Grand Rapids, Michigan follows this distribution. 15.9% of people are under the age of 10, 14.9% are between ages 10 and 19, etc., all the way through 55 plus. You should be able to verify that all of these percentages do indeed add to 100% if you take the time to add them up. Now suppose that you have visited Indianapolis, Indiana, which is relatively close to Grand Rapids, and you are curious if the distribution of ages is more or less the same as Grand Rapids, or if perhaps the age distribution of the city of Indianapolis follows a different distribution, with different percentages than the ones that we see here. To see if the distributions are the same or different, we could take a sample of individuals from Indianapolis and estimate the percentages in each of the 5 categories. If the percentages are more or less the same as what we see in Grand Rapids, we will conclude that the age distribution of Grand Rapids fits the age distribution of Indianapolis. If we get significantly different percentages in the 5 categories for our age distribution, then that will indicate that the age distribution of Indianapolis follows a different age distribution than Grand Rapids. This process is what we call the chi-square goodness of fit test. Now, as mentioned earlier, we need the degrees of freedom in order to use the chi-square distribution. The degrees of freedom for the chi-square goodness of fit test end up being just k minus 1, where k is the number of categories you have in your distribution. So in our case, since we have 5 different age groups, the degrees of freedom will just be 5 minus 1, which is equal to 4. The null and alternative hypotheses for the chi-square goodness of fit test always take on the following form. The null hypothesis is that the population in question fits the given distribution, and the alternative hypothesis is that the population in question fits a different distribution. Now, of course, you will need to modify these hypotheses to fit the specific problem that you are completing. So for our age distribution example, the null hypothesis is that the age distribution in Indianapolis fits the age distribution of Grand Rapids, and the alternative hypothesis is that the age distribution in Indianapolis does not fit the age distribution of Grand Rapids. At this point, we would be ready to take a sample of Indianapolis residents to see if our observed quantities match the percentages given by the Grand Rapids distribution. Let's say we take a random sample of 500 Indianapolis residents and find that 71 are under 10 years old, 64 are between 10 and 19, 120 are from 20 to 34, 121 are from 35 to 54, and 124 are 55 or older. we would like to determine if the distribution of Indianapolis ages is different or the same as the distribution of Grand Rapids ages. I will use the same 3 steps of any hypothesis test that I've used in other videos. The first step is the null and alternative hypotheses, which we have already completed earlier, so I have pasted those hypotheses here. The second step is calculations. This is where I will utilize the TI-84 calculator. Press Stat and then Enter to get to the stat list. Enter in the observed values into list 1. The observed values are the values that you observed from your sample. So in this case, the number of individuals in the 5 age groups from Indianapolis. So we have 71, 64, 120, 121, and 124. Next, in list 2, we need to have the expected number of individuals in each age group, assuming that the age distribution in Indianapolis is the same as Grand Rapids. In other words, if we took a random sample of size 500 and the distribution of Indianapolis ages was identical to that of Grand Rapids, we would expect, for example, 15.9% of individuals to be under 10, 14.9% to be between 10 and 19, etc. Now to calculate the expected values, simply multiply 500 one at a time by each of the percentages. For example, take 500 times 0.159, the decimal equivalent of 15.9%, and you should get 79.5. 500 times 0.149 equals 74.5. 500 times 0.265 equals 132.5. 500 times 0.251 equals 125.5. And 500 times 0.176 equals 88. Just take a second to compare the numbers to make sure you understand what they mean. The first list represents the observed values, the number of individuals in each of the 5 age groups from our sample of 500 individuals living in Indianapolis. The second column tells us what we should expect the first column to have been if the distribution of Indianapolis ages followed the same distribution of ages that Grand Rapids does. So, for example, we expect to see around 79.5 individuals under age 10 in Indianapolis from our sample of 500 if the Grand Rapids and Indianapolis distributions were the same. We actually had 71 observed in our sample, so relatively close but a little bit off. We should have expected to see 74.5 individuals from age 10 to 19 in our sample, but only saw 64, so even a little bit further off in that one. When there is a large discrepancy between these two columns, that will be associated with a lower p-value, and therefore evidence in favor of the alternative hypothesis, that the age distributions are different between the two cities. Okay, now press Stat, arrow over twice to the right to get to the tests, scroll up, and you should eventually get to the chi-square GOF test, or goodness of fit test. Press Enter. As long as you enter the data into lists 1 and list 2, as instructed earlier, you shouldn't have to change the observed or expected lists here. Enter the degrees of freedom, which are 4, which we calculated earlier as the 5 categories minus 1. Press Enter over Calculate, and you will have the chi-square test statistic of about 18.46 and a p-value of 0.001. Now we are ready to make a decision and write a concluding statement. Let's assume that we are using a level of significance of 0.05. As the p-value of 0.001 is less than or equal to the level of significance, we reject the null hypothesis. Our conclusion is that, at the 5% level of significance, there is enough evidence to suggest that the age distribution in Indianapolis does not fit the age distribution of Grand Rapids. Okay, that completes the test using the calculator, but just in case you were curious how to complete the test by hand, once you found the column of expected values, you would need to plug into this formula. The sum of observed values minus expected values squared divided by the expected values. All this means is, for each of the 5 categories, or however many categories you have in your problem, take the observed value, subtract the expected value, square your answer, and then divide by the expected value. At the end, add up all of your values together and you will have the chi-square test statistic. Here are the expected values that we calculated before on the calculator, which you would need to do by hand. Remember, we got these by taking the percentages and multiplying by our sample size of 500. So 0.159 times 500 got a 79.5, 0.149 times 500 got a 74.5, etc. This is what the calculation looks like for us for the chi-square test statistic. Take 71 and subtract 79.5, square your answer, and then divide by 79.5, then add to that 64 minus 74.5 squared divided by 74.5, etc. for all 5 categories. When you add all of those values together, you get what is called the chi-square test statistic of 18.46. To find the p-value, we need to calculate the area in the right tail of the chi-square distribution, greater than 18.46. You can do this using probability tables or computer software, but the TI-84 calculator has a function called the chi-square CDF function, and that can help us find the p-value. To get to chi-square CDF, press second, then press distribution under the vars key, scroll down until you see chi-square CDF, and press enter. The lower bound is the lower bound of the shaded area on our graph, where the shaded area starts, which is the chi-square test statistic of 18.46. The upper bound of the shaded region is, well, technically there is no upper bound. The shaded region goes on forever in the positive direction to infinity. But if we put 1000 here, that is plenty large enough for our calculator. The degrees of freedom are 4, as we already stated. Press enter over paste, and you will see the function output. On an older calculator, match this output with commas. Chi-square CDF, 18.46, comma, 1000, comma 4. Press enter, and you should get the same p-value as before, 0.001. This is the area in the right tail of the distribution. From there, you would make your decision and write a concluding statement as we did previously. Alright, my friends, that completes our discussion of the chi-square goodness of fit test. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.